Yeah, so now that I've talked about, how do I make that? Oh, there we go. Yeah, so now that I've talked about radioactivity and the decay equations, we're going to spend the next few lectures talking about mass spectrometry, how we actually measure the parent isotopes and the daughter isotopes to actually do our calculations. And the reason we're going to spend so many lectures on this is that it's quite important. Obviously, if we can't measure things precisely, we're not going to be able to calculate meaningful geologic ages. And it's a complicated thing to do, and there are many different kinds of instruments, all tailored to different techniques, different ways of measuring things for different systems, different geological problems. And because there are so many different ones in use, and they're all quite specific, we're going to spend quite a lot of time on this. But what I'll talk about today is kind of the general overview of mass spectrometry, because there are some parts of the mass spectrometer that any mass spectrometer we look at will have some of these components. What's really different between different techniques and different mass spectrometers, for the most part, is how you actually ionize your material and put it in to the mass spectrometer. But the actual part about the mass separation is more consistent between different mass spectrometers. So we'll focus on that first, and then we'll talk about different applications, different kinds of instruments. Shown here is just, this is what's called a secondary ion mass spectrometer. I used a picture of this because they're huge. It takes up half this room, and it's more impressive than some of the other ones. I mean, some of them are small enough they could fit in a box like this. So I want to talk a little bit about the historical development. So the first important historical development, of course, was the detection, the understanding of radioactivity, that this is something that occurs. But in terms of the actual technical side of things that led to mass spectrometry, it was the work of Eugene Goldstein in 1886. What he did is he made a tube, and this tube contained a gas, and he applied a negative charge to a plate with holes in it, and then on the other side of the tube was a plate that was positively charged, and it would produce electrons that are then attracted to the anode here, and positive ions that are then attracted through these holes in the cathode. But he didn't know at the time what they were. It produced some glowing beams that were going through these holes. And he argued that this was like photons. It was a kind of, I mean, they didn't really know what photons were yet either, but he argued that it was some kind of wave, a beam of something rather than actual particles. Whereas in reality, what it was producing was positive cations that were then passing through these holes in this electric field. In 1898, Wilhelm Wien found that a strong electric current that is applied to this so-called canal rays. So Goldstein called them canal rays because they were passing through a canal and they looked channelized. What he did is he has his anode down here, his gas in here, the cathode is here, and then there's a small channel within the cathode that allows the particles to pass through. And then he has an electromagnet in this second chamber here. And what he found was that when these canal rays pass through this hole into the other chamber and into the electromagnetic field, they were actually deflected. And how much they could deflect depended on their mass to charge ratio. So how massive the ion is, and whether it's a 1 plus ion or a 2 plus ion or a 3 plus ion or a 1 minus ion. And this is really the basis of mass spectrometry here. The idea that you can actually separate out masses using an electromagnetic field. So this was the first real major development. And also it was proof that these are actually particles, not rays. Then
when they just raise it, they have no mass, right? Then they wouldn't pass the cathode after all, right?
If they're focused, they should still be able to pass through that small slit. Some of them, a percentage, I don't know, 5% or something. But then they would hit the back of the tube and not be deflected by the magnetic field.
But
and
they still need mass for it, because otherwise they would just neutralize the cathode, right? It's the same process during the reflection.
Yeah, you would think. I think there's a certain probability that some pass through the hole, but it's very minor. And Goldstein actually did experiments where he applied a magnetic field, and he claimed that he couldn't deflect the beams, which is why he said that they were rays and not particles. But he clearly did his experiments wrongly. So the next major development was in 1912, when J.J. Thomson and F.W. Aston channeled neon ions through an electromagnetic field, and they then channeled them onto a photoplate. And this is the photoplate here, where there are different parabolic curves that are imprinted on the photoplate that correspond to the different ions and isotopes that were in the gas. Of course, they tried to use it with a pure neon gas, but there's other things as well in there. They were actually, for the first time, able to separate out conclusively different masses. So we can see here, this one is mass neon 22, and this is neon 20. But we can also see there's a doubly charged neon that forms this beam here. And then we have mercury and carbon monoxide and CO2 and other things. This was not a pure gas. But this was the first time this was done. And the difference between this and what Wilhelm was doing was that it was done under a vacuum with a photoplate. And the addition of the vacuum really helped the ability to be able to identify these. Because if you don't have a vacuum, then you have too many particle-particle interactions and particles slamming into each other and deflecting each other, and then the ions don't actually make it to the photoplate. And we'll see this is also why we put mass spectrometers today under very high vacuums. The next real development was in 1917 by Arthur Dempster. He was a Canadian-American scientist. He constructed the first mass spectrometer with this kind of geometry, where we have this U shape, a circular geometry. And what he did is he put a focused ion beam into this half circle, and it's under a magnetic field. And depending on how you tune the magnetic field, you get the ion or the isotope that you want through the detector, whereas the other isotopes slam into the wall. And today, we still base our geometry and our designs on this basic principle that Arthur Dempster developed. Francis Aston was perhaps more famous during this period because while he was also developing mass spectrometers in the UK, and he was a more prolific writer. Arthur Dempster was a professor. He had lots of students. He had lots of lectures to give and classes to teach. Francis Aston was just a research scientist, so he had nobody bothering him. And he discovered 212 naturally occurring isotopes, and he had all of the time to write the books that claimed that he was doing the real research. But this is the mass spectrometer that he developed. Here is where the magnetic field is that would separate the ions. But the kind of geometry that he developed is not what we use today. So his mass spectrometer wasn't as good as Dempster's, but he had more time to tell people that it was good. But the real huge breakthrough with Dempster was that he developed the first doubly focused mass spectrometer. And I'll talk in detail about what it means to doubly focus. But what he did is he combined a magnetic field part with an electric field part. And the electric field makes sure that all of the ions come through at the same speed, so that when they get into the magnetic field, they're all deflected in a uniform way. And then they hit a photoplate, and what he was able to discover was uranium-235. Uranium-238 was already known because it's the more abundant one. But uranium-235, because it has a potential to mass interfere, if you can't get these values on the photoplate far enough apart, you can't see the difference between 235 and 238. And it produces, as you can see, a much narrower slice on the photoplate because it's so much less abundant. And it wouldn't have been possible without this kind of doubly focused instrument. And then the final important development in terms of making mass spectrometers that look like the ones we use today was in 1940, Alfred Neer, who pictured here with one of his mass spectrometer tubes, designed, rather than having a half circle, you could only have like a 60-degree turn in your magnetic field or a 45-degree turn. This allowed for more accurate and more portable instruments because as we'll see with the equations that govern how we can separate isotopes, that the ability to separate masses depends on the geometry, on the radius. So the bigger the mass spectrometer you can make, the bigger the magnet you have, the longer the flight path, the more separation you're able to get. And the most extreme example of one of these things is there's something called a megasims, where the entire basement of a building is one big mass spectrometer. And it's due to these geometry constraints. But Neer was one of the first people who was able to make something in a geometry that was usable for everyday isotope analysis. So what is a mass spectrometer? You already saw some important pieces of it in the historical development part of this lecture. First of all, we need an ion source. We won't talk about that much today because, as I mentioned at the beginning, the different kind of techniques we use, the biggest difference in them is that we use different kinds of ion sources. But there is always some kind of source that produces ions because these things have to be, in order to separate out a mass, they need to also have a charge so that they can be affected by electromagnetic fields and deflected into a detector. So we always have some ions that are produced. They need to be accelerated and focused into a beam that we can work with. And that's what these extraction and focusing lenses with the slits do. There is usually some kind of electrostatic analyzer that filters for their kinetic energy, or really filters for their velocity. There is usually some method used to separate out the ions by their mass to charge ratio. In this picture, it's using a magnetic field. There are different kinds of electromagnetic fields that are used for this. And in some cases, there's one technique that doesn't use one at all. And we'll talk about these different kind of mass separation techniques. But there's always some way that separates the mass based on the mass to charge ratio. And then, of course, at the end, we have to have some kind of detector that quantifies the magnitude of the beam coming in at each mass. And the whole thing needs to be under a high vacuum. Usually the vacuum is higher in the back and lower at the front, which also kind of helps to draw the ions out. But if we have our ions colliding into gas molecules, then they're not going to make it to the detector. So it needs to be under a high vacuum. So first, I'll talk about the extraction and focusing of ions. So once the sample is ionized in some way, the ions have to be accelerated and focused into a narrow beam. This is usually done by using a series of metal plates with cascading voltages. So here are two pictures of the same setting, same apparatus, but slightly different way of looking at it. What's shown here are these big black bars are the cross sections of the metal plates to which different voltages are applied. And the thin lines show the electric field generated between the plates. What these numbers are is the fractional reduction in voltage. So we have a high voltage up here and the ground down here. And the ions, because they're mostly positively charged, will be accelerated towards the ground at the bottom here. So we have a high voltage ionization source at ground here. It's something like usually on the magnitude of a few thousand volts, 1 to 10 kilovolts is usually the ionization difference between the region where it's actually ionized and where it's extracted. And the ions leaving the source have a kinetic energy that is equal to the accelerating voltage. And because we apply a certain accelerating voltage, we can then calculate the kinetic energy and the velocity of the outgoing ions, which is actually a big part of your homework. And the ions, what we're actually seeing here is the actual path that the ions take. So they're not deflected and focused in a straight line. There are some that veer off entirely, and we have some slits that prevent those from traveling through. And the ones that aren't deflected wildly and are able to travel through the slits are all moving in the same direction, and this is what we call our ion source. So how does this actually work? So we have here our positive plate. We have some ionization chamber that's producing positively charged ions. We have this positive plate here, and then we have a negative plate, and we have a slit that runs through them that allows our ions to travel through, and they're going to leave at a certain velocity. And our electric field is causing them to move from the positive to the negative, or well, from the high voltage to the ground. So the force acting on them is equal to Z, which is the ion charge. The ion charge is in multiples of 1.60219, 10 to the negative 19 coulombs. One of those is an electron. So if your ion charge is removing one electron, it's that number. If you have a doubly charged ion, it's double that number. Triply charged is triple that number, and so on. So we have our charge times our electric field, and that is the force that's applied, where E is the magnitude of the electric field, and this is a vector. The acceleration is given by the mass times the velocity squared over 2 times the ionic charge, and that is equal to the voltage difference. So the reason I rewrote it this way, and you'll see this reorganized in different ways in different books, but the reason I wrote it this way is this delta V is something that we apply. So we apply a voltage difference in our instrument to extract it. And that allows us to, for a certain mass and a certain charge, have a certain velocity of ions coming out. And the mass is, of course, we can calculate from atomic mass units, and if we want to we need to convert into kilograms. This is something you'll do in your homework. And this is the conversion rate from Daltons to kilograms. So we can rewrite this in terms of if we apply a certain voltage difference for a given mass with a given charge, what our velocity would be. If we have, and that's for a perpendicular path, but of course, you can have a non-perpendicular path where r is the radius of the curvature of the ion trajectory. And because not all of the ions are having a perpendicular path, not all of the ions are this one in the middle that's going straight through, some of them get deflected over a certain radius and then focused into a collimated beam. So some of the ones that are deflective, of course, they hit the sides of the detector or they hit the slits, but a large percentage of them, we want as many of them to be able to be focused into a central beam as possible. And we can see here, this is actually the focal length, and then they have some spread after that. But you try to focus as many of them as possible. And so that they can pass through what we call the source slit. And the source size and detector slits help define our mass resolution, because each time we have some particles being lost, we're losing part of our signal. And there are other stages of the mass spectrometer where things are deflected and lost. So you want to try to get, especially if you're trying to analyze something that's not very abundant, you want as many ions of that isotope to make it to your detector as possible. And we're only talking about the beginning here. But you can see here that in our path, only a certain amount of these ions that are able to be put into this collimated beam actually make it through. So the next part is the electrostatic analyzer. This is called the Near-Johnson geometry because the electrostatic analyzer comes before the magnet. There are also geometries that I'll talk about in a bit where the electrostatic analyzer can come after the magnet. They have similar effects and produce similar things, and different companies decide to make them in different ways. The idea with the electrostatic analyzer is not all ions leave the source with the same velocity. So, because if we go back to our equation, we have m over z times the velocity, right? So for different masses, we'll have different velocities. Lower m is a higher velocity. You'll realize this when you do your calculations for the homework. So if you have a material with different kinds of isotopes in it, different isotopes will have different velocities when they leave the source. The same mass, because it's the mass to charge ratio that accelerates them, the same mass but with a different charge will also have a different velocity. So if you have a doubly charged nickel 58, that will have a different velocity than a singly charged one. And also they can be deflected in an imperfect vacuum. So what's shown here is the velocity spectra of carbon, antimony, titanium, and vanadium from some experiments. And we have a main peak here that is the main isotope that is passing through and the velocity is being measured, but we see that there's a large tail on it, and those tails have other peaks of different particles or the same particle but with different velocities, right? And we want a single velocity in our material to come through. So how we do this is we apply an electrostatic analyzer. It's two concentric curved metal plates, and there's a voltage that's applied across them. So again, we have our equation that I showed previously, where we have the force is equal to the charge of the ion times the electric field. These curved plates have equal and opposite potential, so one of them is the cathode, one of them is the anode, and the difference between them is equal and opposite. Ions with different kinetic energy but the same trajectory are then dispersed independent of their mass to charge ratio. So we can do this in two ways. We can either have a slit or energy window at the exit of the electrostatic analyzer, and we can adjust its width and position in order to select a certain range of energies. Or we can have a slit that's at a fixed position, but then change the electric field to let out certain ions. So this is what it actually looks like. So we have not just an electric field, but a magnetic field. We have our ions passing through at a certain velocity. There is a negatively charged surface and a positively charged surface, and the charged particles are in this case being deflected upwards. And at the moment, there is no velocity term. This is the part of the equation that deals with the fact that we have the electric field. Now, there's also a part of the magnetic field, and the force on the magnetic field is in the opposite direction. I don't know if you've ever heard of, we call it in the US, the right-hand rule, which is if you have your magnetic field, in this case it's going into and out of the board, and you put your hand like this, where this is the direction the particle is traveling, your palm is facing in the direction of the magnetic field is acting, then the actual force on the particle is in the direction your thumb is pointing. And that is how when you solve this cross product, where it's the charge times the cross product of the velocity times B is usually used for the magnetic field, then you get a certain amount of deflection in the down direction. So depending on how fast the particle is moving is how much the magnetic field acts on it. So the electric field part doesn't depend on the velocity, but the magnetic field part does. So the electric field part is attracting the ions in this direction, and the magnetic field is attracting them in this direction. And depending on which particles you want to let through, you can adjust the electric field and the magnetic field so that they balance for that specific particle and allows it through. Whereas the other particles, at a different velocity, they're pulled more in the down direction, and the particles with a charge that you don't want are pulled in the up direction. And then only the things that you've tuned it for actually make it through the exit slits in the end. So if we have no deflection, then our energy pulling the ion up and the energy pushing it down are equal, and they pass through in a straight path. And this can only occur if we take our equation that has the velocity component for the magnetic field and make it equal to the equation for the electric field. We have Z times E is equal to our charge times the velocity times the magnetic force. If we rearrange this, then the velocity has to be equal to this ratio of the electric force over the magnetic force. So we can tune this to let only a specific velocity through. And this is depending on what we're interested in. And in the homework, I'll have you calculate different velocities for what is escaping the ion source. And then you can think about, okay, if a uranium atom has this velocity or strontium atom has this velocity, how do I tune the electrostatic analyzer to let that velocity range through and not the other ones? So usually if you want to analyze multiple isotopes or something like this, you would put this somewhere in the middle of the different velocity range that you're expecting. And it filters out a lot of the ions that are at different velocities because they interacted with something. And the last thing I'm going to say before we finish for today, wait, 1, 2, 1, 3. No, we still have 30 more minutes, right? Yeah. Sorry, I'm getting ahead of myself. Again, ions that are too fast and ions that are too slow are not let through the slit at the end. What this means is that now we have a second stage at which we've focused, and now we've let through things of only a certain velocity, but we're also losing things. So again, each step is decreasing our sensitivity in the end because we're losing a certain amount of ions. Because even if we do, as we saw in the graph before, are only measuring carbon and letting carbon through, there are some carbon atoms, some carbon ions that don't have the same velocity because they hit the wall of the detector and or the wall of the mass spectrometer and we're deflected in some way. Those aren't being let through. So each step that we have an analyzer and a slit or an accelerator, something isn't getting through. So it's important to tune all of these in such a way that you let as much through of what you want to analyze as possible, otherwise no ions of the isotope of interest actually make it to the detector at the very end of the mass spectrometer. And problem 3 in the homework, I'll have you changing the position of the slit so you can see how that affects and lets things through. So a bit more on why we need the electrostatic analyzer is because ions with different kinetic energies broaden peaks and produce tails on the mass scan. So if we're looking now at the detector, what it's analyzing at the very, very end, here we have a mass scan over the range of voltages. Actually, it measures voltages in the detector, at which we would expect to see uranium-236 and uranium-238. And uranium-236 is a really, really, really minor isotope of uranium. So we see that it has a small peak that we've zoomed into, but notice that it's not flat. When there is no ion beam allowed through the instrument, we have this gray line, and then the wiggles in the gray line are just the background noise of the detector. But once we let the uranium atoms isotopes through, we see our 236, but there's also this slope here, and that slope is due to the tail of the 238 peak that's nearby. So our actual intensity of our 236 peak is a combination of the actual 236 that we want to measure plus the tail of the 238, and this increases the amount of 236 we think we have if we don't correct for it. So this tail is caused by this wider distribution in velocity that we need to filter for. So this affects what we call our abundance sensitivity, and this is the amount of stray ions that scatter under the peak of a nearby isotope. So the difference between this peak with the interference and this peak without is the abundance sensitivity. So the ability, if we put an electrostatic analyzer before the magnetic sector, the ability for the magnetic sector to focus the ion beam is going to depend on how well the electrostatic analyzer is able to decrease the energy spread of the ions coming into it. And the deflection within the magnetic sector, as we'll see in a bit, this is where we actually do the mass separation. It's dependent, it's proportional to the momentum. So we want all of the ions, once they reach our mass analyzer, to have the same momentum as much as possible. So this is what we call a doubly focusing mass spectrometer when we have an electrostatic analyzer, because the electrostatic analyzer focuses the beam by the kinetic energy, and then we have our mass spectrometer part that actually focuses it by its mass. So I mentioned we can place the mass analyzer before our, we can place our electrostatic analyzer before the mass analyzer, before our big magnet. This helps the mass analyzer focus better because all of the ions that are going into it have the same momentum. So they're going to be deflected in the same way by the magnetic field in the magnet, in the mass analyzer. You can also place them after the mass analyzer. And what this does is anything that went through the mass analyzer and was not deflected in a uniform way gets filtered out by the electrostatic analyzer afterwards, because you have some ions that collide with the side of the magnet, that collide with each other, they lose energy, and then they reach this the electrostatic analyzer after the magnet. It filters out all of the things that lost energy, and then the electrostatic analyzer just simply sends things with only a specific momentum into the final detector. So in both ways, they kind of, the end product is similar, and people argue about whether it's better to have the electrostatic analyzer before or after your mass analyzer. But they produce similar sensitivity results in the end in your ability to measure isotopes. So the last thing we're going to look at, well, the second to last thing we're going to look at then, is the actual magnet, the mass analyzer, where we're actually separating out the masses we want to analyze from the masses we don't. So how a magnetic sector mass analyzer works is, so we have an ion that's traveling in a magnetic field that's aligned perpendicular to the path that the ion is traveling through, and we want to deflect it. So we have a similar equation to what we had earlier, where we have it, I've rewritten it in terms of mass over charge, because that's what we're actually working with. B squared is the magnetic field. R squared is the radius of the magnet. So we have our magnet here. This is a 45-degree portion of a circle. Our radius is somewhere over here for our travel. So we have the radius of the curvature as R, and then we have 2 over the velocity. And again, because we have velocity in this equation, that's why it's so important to have a uniform momentum coming into here. Because even for the same mass and the same charge, if the velocity is different, then it will affect the radius of their deflection. So the radius followed by an ion, because we have velocity in here, is proportional to its momentum. And we can rearrange this to calculate the radius of the path of the curvature that the deflected ions will take. And that's equal to the square root of 2 times the mass times the velocity over the over the charge times the magnetic field squared. Most mass spectrometers nowadays use either a 90 or a 60-degree section of the circle, and the magnetic field refocuses the diverging beam and allows it to pass through another detector slit. So in this example here, we have our exit slit. The 86 strontium is being, because it has a lighter mass, it's being pulled more strongly by the magnet, and it hits this part of the exit slit and doesn't pass through. The 88 strontium has a greater mass than 87. It's not affected as strongly by the magnet, and it hits the other side. And you can tune the magnetic field and the position of the exit slit, again, to let in the mass that you want to analyze. And this is what allows us to actually analyze our isotopes. Here's just a slightly different way of looking at it. So we have our source, and that source is going to spread out. In our magnet, the ions traveling at the center line will ions diverging from the center line will traverse different distances. So wider path ions are going to curve more than inner path ions. And the magnetic field, not only does it distinguish between masses, but if we have the same mass traveling these 3 different paths, it takes that same mass and focuses it onto the detector. So this allows us to not lose particles that don't take a central path through the magnet. So it separates out the masses. That's part of its job. The second job is to actually focus them onto the detector.
And isomers, the problem?
Yes, yes, there are. So that's actually what this is. So here we have, I want to talk a little bit about what the exit slit actually does. So So we can have slight variations in an imperfect magnetic field strength or accelerating voltage. This causes the exact position of the beam to wander, so that's one problem. The other problem is that you can have mass interferences from isobars. So for example, this is an analysis of 87 strontium on a secondary ion mass spectrometer, or SIMS. And here is where the mass of the 87 strontium should be, but because we're measuring an apatite, there's also an interference of calcium phosphate on that mass. And this calcium phosphate ion has a mass of 86.9313, whereas the strontium has 86.9089, so they're really quite close. And this is plotted here in relative mass, and then we have our counts per second. And this is with different exit slits. So if we have a really small exit slit that is the same size or smaller than the beam that's going into it of what you actually want to analyze, then you get a really pointy peak. If it's too big, then the broadening of the peak you want to analyze starts to overlap with the potential interference next to it. So typically you want to choose something. You don't want the slit to be too wide because then it lets in too many different things. There are, even for isobars, there are slight differences in their mass. There's a slight difference between strontium 86 and strontium 87 and rubidium 87. But there needs to be a big enough difference that those peaks are resolvable. That's I talk about this in problem 4. I ask you to calculate the mass resolution needed to distinguish 235 uranium from 238 uranium, and then strontium 87 from rubidium 87. And you'll see what kind of problems you run into. What we ideally want is somewhere in between. So for this spectra, a slit of 173 nanometers is ideal. It provides enough of a flat top where if your voltage is not quite precise, what you're actually analyzing will wiggle a little bit in the x direction on this mass scan. You want to have a broad enough peak that you don't accidentally measure on the side of it, because it can also drift throughout the day. So you want to make sure you put at the beginning of your analysis your mass that you're analyzing on a position in the middle of a flat peak of the mass that you want to analyze, so that if there's any variation, you don't measure somewhere off the peak.
Is the tuning process getting harder when you decrease the slit size?
If you decrease the slit size too much, then the mass peak becomes too pointy, and then any slight variations in the voltage of the detector are going to measure off the peak. And then you get really imprecise. You're still measuring something, but it's going to be very imprecise. So you want a broad enough peak, but you don't want it to be too broad that you have overlaps. And again, this is something that you tune on a known material, and you change the position of the exit slit, the magnetic field, all of these different parts of the mass spectrometer, you tune to get the best looking peak. And usually this is what you sit and look at for half a day until you get what you want. And usually with the interferences, these are all known interferences, and it depends on the material. For example, if we were measuring a feldspar instead of an apatite, we wouldn't have this calcium phosphate interference. And it also depends on the instrument. The secondary ion mass spectrometers produce a lot more interferences than an ICP-MS would. And we'll talk about that when we talk about the different kinds of sources. So up until now, I mostly focused on what we call magnetic sector instruments. But there are also quadrupole mass analyzers. How these work is that they have 4 parallel rods that are aligned around a central axis, and static potentials, DC voltages, are applied to some rods, and alternating radio frequency voltages are applied to the other rods. And then they switch positions, and one rod pair always has the opposite polarity of the other. And by switching between these rods, it creates a fluctuating electric field. Typically, the fluctuation is at frequencies of around 1 megahertz. And a stable ion with stable trajectory for a certain mass-to-charge ratio will pass through the middle of this, whereas ions that are not stable will be deflected. Right? So you have some kind of sinusoidal path that the ion you want to measure is taking through that field as the polarity is switching on the quadrupoles. The wavelength is proportional to of the trajectory that it's taking is proportional to the mass over charge ratio. And if you have an ion that has a too large or a too small mass to charge ratio, it's deflected out of the quadrupole. For an ion to make it through the quadrupole, it needs to be stable in both the x and y directions. So here is a graph showing the regions in purple of the y stability, and green in the x stability, and where those overcross is where you're going to allow the ion of interest to pass through. And typically we take the one that occurs at the lowest voltage because it provides the most wide region of stability in both the x and y direction. So we call this typically the first stability region. And the stability region is dependent, of course, because it's path dependent on the mass to charge ratio. And we can plot the stability regions of different masses on a single axis, which is what's done in this diagram here. So here's the RF voltage, here's the DC voltage, and for mass 1 and so on, these regions are the area at which that mass can pass through stably. Now, typically we want to not just measure one mass. We can actually cycle through different RF and DC voltages to then analyze a bunch of different isotopes, right? So instead of, for uranium lead geochronology, we can analyze the different isotopes of uranium, the different isotopes of lead, but oftentimes because these instruments can cycle their electromagnetic field so quickly, we can analyze like 40 different isotopes. And then you can get not just what you're trying to use for geochronology, you can also get the trace elements as well. Which is one of the advantages of this instrument. The problem, magnetic sector instruments, you can also cycle through different magnetic fields, but there's a longer settling time. So you can't cycle through isotopes as quickly and measure as many different isotopes as you can with a quadrupole mass analyzer. So typically what you do is you cycle, you ramp linearly the RF voltage and the DC voltage with time. And as you do that, you intersect these regions of stability in a way that as you hit that peak of stability in the RF versus DC plot, that occurs in a place where there's no overlaps. And you can tune this in a way that rather than intersecting somewhere like here, you would intersect the very peak. So you intersect at a narrow ratio of DC to RF at which only a certain isotope is going to be passing through. And this is what you do for tuning. So you want a scan that does not somehow cross two stable regions simultaneously. And then what you get, if you do that, is on your signal, through time, you get really sharp peaks when you're only letting the mass through that you want. And then you cycle through the DC and RF voltage multiple times, and then you get a stable signal for each mass. And this is how you optimize for the best resolution. You have to find the right interplay between the RF voltage and the DC voltage that allows the whole series of masses you want to analyze through sequentially. The last one I'm going to talk about before in the last couple of minutes here is time of flight mass spectrometry. Earlier when I showed this equation, velocity is equal to the square root of 2 times the charge times the voltage difference divided by m. And the voltage difference is again from the acceleration you get between the ionization source and the exit slit at the beginning of the mass spectrometer. Well, mass is in that equation. And it's related, and charge is in that equation, and velocity. So different masses and with different charges will have different velocities. So if you have a really long mass spectrometer, such that there's enough time for those different velocities to give very different paths, very different separation between different masses, you can actually analyze them based on their velocity, because they will arrive at the detector at different times. So lighter masses have faster velocities and they'll arrive first. Heavier masses will arrive later. The longer the flight path you have, the more they have time to separate. So oftentimes these mass spectrometers, there's one in the chemistry building. It's huge. It takes up like 2 of these tables. So it's like 2.5 meters long. 2 to 3 meters is normal length for these. And what you need is you need a short pulse. So you have a nanosecond or femtosecond duration in your pulse. And then you turn on your detector, and the light isotopes hit first, then the heavier and heavier and heavier isotopes. And you turn off your detector, and you have it cycle for each pulse that comes through. Because eventually, everything is hit the detector, and then you start the next pulse. The nice benefit of this kind of mass spectrometer is that every isotope in your material will hit the detector at some point sequentially. So you can measure with a single pulse everything that's in your sample. So you can, that's really nice, because with these other techniques you have to cycle through the voltage or cycle through the magnetic field in order to separate out different isotopes. And you can only do that so fast, especially with a magnetic sector instrument, and that limits how many different isotopes you can analyze. With this, you can analyze everything that passes through. However, the resolution is limited by the time duration of the pulse, and also the time of flight separation. It's most commonly used for imaging techniques, so they're using it over there to image like nanoparticles in like mice brains and things like this to look at environmental contaminants and things like this. So it's used a lot in biology. It doesn't have a good enough sensitivity for most geochronological uses now. So it's only very rarely used in geochronology. The book said never, but I put rarely used because I wasn't 100% sure that nobody has tried it. And the very last thing that I'm going to talk about, and sorry I'm going to go over like 1 or 2 minutes because this is in your homework, is the mass resolution. So you have to be able to separate out the different masses in your detector. So the mass analyzer separates out the ion beam into discrete beams for each of the isotopes of interest. The separation needs to be sufficient enough that you can tell the mass of interest from the next closest mass. So here's just one of the images from the earlier example of strontium with this interference of the calcium phosphate. That needs to be separated enough that the calcium phosphate doesn't add to the strontium that you want to measure. Otherwise, you get too much 87. So the ions from the nearby mass should never enter the detector at the same time as the mass that you're interested in. The mass resolution is defined as the width of an individual isotope beam divided by the difference between the masses. So our resolution is equal to m divided by the difference between two masses. And you'll calculate that in the homework assignment for the problem 4. In practice, what we do is we look at our detector, we scan across the masses, we find these flat peaks, and we can calculate it actually from our mass scan. So mass 1 and 2 are the mid positions of two adjacent peaks. The delta M is the difference between those two midpoints. And we also have to account how wide those peaks are, because they might be able to overlap, right? And that's our delta M. And then we can use this equation 3.12, and that's the equation that we use in actual practice when we do a mass scan to calculate if we have sufficient mass resolution. And you do a mass scan by varying the strength of the magnetic field, either in a sector field mass spectrometer, so the ones with the big magnets, or you change the RF and DC voltage in your quadrupole mass spectrometer in order to do a mass scan. And then you tune the laser, or sorry, not tune the laser, tune the mass spectrometer until you get a resolution that's sufficient for your problem. And typically, we measure either at 10% of the full peak or 50%. So you measure at half the peak in order to calculate the mid position and the delta M. But what I'll have you do in the homework is simply using the first equation, and you can calculate a rough mass separation by just considering the differences between the masses. So I have you do this for uranium and also for 87 rubidium and 87 strontium. And you can calculate roughly like how far apart what kind of resolution you would need to actually analyze those isotopes in a mass spectrometer. And you'll see how different it is for the two different examples. And next time I'll talk about detectors, and then we'll talk about different ion sources as well, different kinds of mass spectrometers, different techniques. Okay, thanks.